All right, today we're going to talk about hot dogs. Well, first, we're going to talk about limiting reactants using a hot dog analogy here. You know, when you go to the store and you buy hot dog buns, there's only 8 of them in there, but yet when you buy a package of hot dogs, there's 10. So the total amount of hot dogs with buns that I can ever make will be 8. So this is sort of a representation of what a limiting reactant chemical equation is like. There's going to be the limiting reactant, the item that you run out of first. So I'm going to use up all my hot dog buns. I'm not going to have anything left whatsoever. But in my pot of water, I still will have 2 hot dogs just sitting there with no other buns. So that is what a chemical reaction and most chemical reactions are like. Well, one of the reactants are all used up, and the other reactant, it's an excess of. Sometimes they do this to help with the chemical reaction to begin with. Sometimes they purposely put in too much of the other reactant to speed up the reaction, to make more product. There's a whole bunch that goes into why that would normally happen, but this is a typical chemical reaction. So, limiting reactant problems versus stoichiometry problems. How do you know the difference? Well, for one thing, limiting reactants provides information about all of the reactants in the question. They'll either tell you the amount of moles of each reactant or the amount of grams, but every single reactant that's in there, you will be given that information. In the stoichiometry problem, they'll only give you information for one reactant. That's it. They may say the other one's in excess, and it seems like they gave you information on all of them, but they're only going to give you an actual value for one reactant. And not all stoichiometry problems give you information about reactants, though, either, right? Sometimes they can start you and say, hey, I made 55.6 grams of oxygen. How much, water is needed to do that, which is one of the reactants. But if we're talking about just comparing reactants information, limiting reactant gives you information on everything. So here I have 2 questions, and we want to divide them. When are they talking about limiting reactants, and when are they talking about stoichiometry? So when I look at this, it says KO2 is used in a closed system breathing apparatus. It removes carbon dioxide and water from exhaled air. The reaction and removal of water is KO2 plus H2O yields oxygen plus potassium hydroxide. But it says what mass of oxygen is produced? What mass of oxygen is produced if you start with 28.9 grams of KO2? Well, all I've ever been given is one of the reactants. I didn't get any information about water, so that's a stoichiometry problem. If you take a look down here, though, I was given that I have 2 grams of ammonia, and it's mixed with 4 grams of oxygen. I have been given all the amounts of the reactants, so this is a limiting reactant. They actually can be solved in the same way. The difference between a stoichiometry and a limiting reactant, one, is to recognize when it is a limiting reactant, because the limiting reactant is used to determine how much product is produced. You have to determine which reactant limits how much of the product can be produced. And when you do that, you are calculating the theoretical yield of that product or products. And once that reactant limits how much product can form, it limits all of the products. People think sometimes it's just one of the products, but if you have multiple products, it limits all of the products and how much can be made. So because it's going to run out first, right? It's going to be all used up. You can't just look at the values that they originally give to you. If they give you 16 grams of hydrogen and 2 grams of oxygen and say, well, oxygen's going to run out first because I have the lesser amount. You can't do that with this. You actually have to do the calculations in order to determine which is the limiting reactant. And it is a reactant. So if the problem was to ask what is the limiting reactant, your answer really should be a reactant. It's in the title of the topic. So let's take a look at our first limiting reactant problem. First thing you need to do is you need to definitely have a balanced chemical equation, which I do. And this says a total of 8 moles of magnesium was mixed with 14 moles of hydrobromic acid. What is the limiting reactant? Second question is, what is the theoretical yield of magnesium bromide? Or I could take the theoretical yield and just say how much magnesium bromide could be produced. Now, you know that this is a limiting reactant because it's asking you to determine the limiting reactant. I could easily never ask this first question and immediately just ask this question. What's the theoretical yield of magnesium bromide? You still have to do the steps that are involved in this question above in order to answer that question. So that's the difference. If a test question would be this one, number 2, you have to determine that these calculations that we're going to do from question 1 have to still be done in order to answer that. So I know this is a limiting reactant because it's given me the amounts of all of the reactants. Now I can determine this in 2 different ways of what is the limiting reactant. There's 2 methods and I'll be explaining that. So first of all, I said make sure the equation is balanced, and it is. I'm going to determine how much each reactant can make of the product. And it does not matter which product that I choose. But I noticed that in this series of questions on the previous slide, it was asking about magnesium bromide. So I'm going to make my math count. I'm going to determine how much each of those reactants can make of magnesium bromide. All right, I'm going to say how much can 8 moles of magnesium make of magnesium bromide. And then I'm going to ask how much can 14 moles of hydrobromic acid make of magnesium bromide. These calculations that are setting up is the same thing what you did in stoichiometry. It's just I need to determine how much each of those reactants can make. The one that makes the least amount of product is the limiting reactant. And by determining how much I make of this product, I'm also determining the theoretical yield because I'm saying 8 moles of magnesium can theoretically make whatever of magnesium bromide. 14 moles of hydrobromic acid can theoretically make so much of magnesium bromide. So in a way, I'm kind of answering both questions if I use this method. All right, so this is a typical setup. I'm going to take moles of magnesium and determine how many moles of magnesium bromide I did that, and I use the molar ratio. I did the same thing with hydrobromic acid, use the molar ratio between those two to determine how much it made. So theoretically, it cannot make more than 7 moles of magnesium bromide, and in this one, it cannot make more than 8 moles. That's the maximum theoretical amount that it can make. So that's why they're called theoretical yields. What I noticed is that the hydrobromic acid makes the least amount of product. So therefore, the limiting reactant is hydrobromic acid. Notice that I had way more moles of hydrobromic acid than I did of magnesium, but he turned out to be the one that was limiting. This is why you need to do the math. So this setup where you take moles of a compound and determine how many moles of another compound it can make, that is still a stoichiometry setup. So when it's saying how many moles of HBr is needed, again, to react, I'm going to do it in another way, and you determine which method you like better. I personally like the previous method because it keeps me in the same framework of all the stoichiometry setups, but some students like this method. So if I know I have 8 moles of magnesium, I can determine how many moles of the other reactant I need. And I did it such as this. I have 8 moles of magnesium, and I did the molar ratio between hydrobromic acid and magnesium. 8 moles of magnesium needs to react with 16 moles of hydrobromic acid. That means that everything would be used up if it was had the availability of the 16 moles of hydrobromic acid. But I only have 14 moles of hydrobromic acid, so therefore I don't have enough moles of HBr to react with that many moles of magnesium. So hydrobromic acid is the limiting reactant. Let's do it with hydrobromic acid, so maybe this will be a little clearer. If I have 14 moles of hydrobromic acid, how many moles of the other reactant does it need? So I do the molar ratio between those reactants, and I find out that it only needs 7 moles of magnesium. So 14 moles of hydrobromic acid just needs 7 moles of magnesium, and I was given 8 moles to start with. So therefore, I have more than enough moles of magnesium. Therefore, magnesium is in excess. That makes the hydrobromic acid then the limiting reactant. You determine which method you like. I'm going to stick with the previous method to stick with that same voice. So I'm going to answer question number 2. It's theoretical yield of magnesium bromide, or how much can MgBr2 be produced. I need to use the information that is the limiting reactant. I'm going to ignore now the information of the other reactant because it's an excess. So remember, the limiting reactant determines how much product can be formed, and the maximum amount of product it can form is going to be 1,288.77 grams of magnesium bromide. So that is the theoretical yield that was determined by using the limiting reactant information. Let's take a look at this equation. I have a total of 45.8 grams of nitrogen gas reacting with 87.5 grams of hydrogen gas. I want to know what's the limiting reactant, how much ammonia is formed, how much of the excess reagent is left at the end of the reaction, and what is the percent yield if you actually measured 41.8 grams of ammonia. So let's break this down. Remember, I could ask any of these questions separately. I don't have to ask these four in a row. I could have immediately just asked, what is the percent yield if you actually measured 41.8 grams of ammonia? Some of these calculations that would have been done in problems 1 and 2 would have still had to be done in order to answer question 4. Okay, so this though I'm asking all 4 questions. So, which is the limiting reactant? I have 45.8 grams of nitrogen and 87.5 grams of hydrogen gas. And I'm going to determine how much each can make of the product. I'm choosing ammonia because it's the only product, but again, if there was more products, I could choose any of them, and I'd still get the right answer for limiting reactant. But I like to, if there is multiple questions, kind of peek down the road and say, hey, they're asking more about this product, so I might as well make my calculations focus on this product to save me time. Luckily in this one, there's just one product, and so I don't have to worry about that. So 45.8 grams of nitrogen gas using the stoichiometry setups can make a maximum of 3.27 moles of ammonia. And 87.5 grams of hydrogen gas makes a maximum of 28.9 moles of ammonia. The limiting reactant then is going to be nitrogen gas because it makes the least amount of product. Once I determine that this is the limiting reactant, I use this information to answer even more questions because the other reactant is an excess. He's the one that's kind of sitting in that hot dog bowl, whatever, or pot on the stove, and just kind of floating around there, right? I got too much in there and nothing else to react with it. Okay, so these setups, remember before I move on to the next slide that these are diatomics. This is why when I say 1 mole of a compound, essentially that they have the double the atomic mass because it's H2 and N2. Just want to make sure I make a statement about that. So we found nitrogen gas was the limiting reactant. So now I want to know how much ammonia is formed. I literally could just take this 3.7 moles that I previously calculated from this point and just change it to grams of that compound. And that becomes my theoretical yield. This 1 mole of any compound is equal to its molar mass is the statement you've already used previously. So this is the maximum amount that can be made. It cannot make any more than 55.7 grams of ammonia. That's it. So let's go to the next question. How much excess reagent is left at the end of the reaction? I know how much I have of each. I know now that this is my limiting reactant, and I know hydrogen is my excess reagent. So if I know that the maximum amount that I can make of ammonia was 3.27 moles, right? That's the maximum amount I can make. I can work backwards and say, hey, I can only make 3.27 moles of this. So how many grams would I need of hydrogen gas to do that? And that's what I've done here. I've taken the amount of ammonia that can be formed and then worked backwards to determine how many grams would have been needed of hydrogen gas to do so. And I found that I only need 9.89 grams of hydrogen gas to produce that many moles of ammonia. I have way more than that in this reaction, right? They gave me 87.5 grams, and all I'm going to use up is 9.89 grams, so I minus that off, and I have 77.61 grams of hydrogen gas that is left over, that's remaining. And this is how you determine how much the excess reagent is left at the end of the reaction. All right, what is the percent yield if you actually measured 41.8 grams of ammonia? And this is an equation. It's called actual yield over theoretical yield times 100 to get it to percent. So when it gives you this amount, this is what you actually made in the experiment. You actually made 41.8 grams of ammonia. It would have to be given to you because you just can't get up and do the experiment on a test or a quiz. Theoretical yields, often you have to determine that, and we already have done that. Some students write this equation as A over T to represent actual over theoretical times 100. Let's look at what our calculations will be. 41.8 grams of ammonia divided by the 55.7 grams of ammonia times 100 gives me 75%. So 25% of it was lost somewhere. Whatever happened, happened, but you rarely ever meet your theoretical yields. We didn't do too bad, I don't think. So let's look at a summary of answering these 4 questions that we started with. First, we recognize that it was a limiting reactant because we were given the amounts of all of the reactants. And we determined how much each of those could make of that product, and we found that the maximum amount we could make was 3.27 moles of ammonia based on the limiting reactant of nitrogen. Then we took those moles and we changed that to grams of ammonia so we could answer the next question of how much ammonia is formed, which is our theoretical yield. How much excess reagent is left over required us to work backwards. It required us to take the maximum amount we can make of this compound and determine how much we really needed of the excess reactant. Anything we didn't need of the excess reactant was subtracted from what we needed, and that's how much unreactant reagent we had. And the last one, what is the percent yield if you actually measured this amount? And we used this formula. So these are the types of questions that could be asked for limiting reactant problems, and I hope that I was clear that I could ask this 4th question and never ask these other ones above it. And to be able to answer question number 4, I would have had to determine the theoretical yield. I still would have had to determine which was the limiting reactant, how much of the product it could form to determine this theoretical yield.